Hello, everyone. We are back with another episode of Computer Vision Talks. And today we have with us Omiros, and we're going to discuss his paper SVL-Adapter, Self-Supervised Adapter for Vision Language Pre-trained Models, which was accepted at BMVC 2022. And as the vision language models are gaining popularity after CLIP, this is our first paper that would be dealing with that area and domain. So we are super excited for the talk. And a brief introduction. Umiros is a PhD student at UCL and is also a researcher at Amazon. So over to you, Umiros. We're looking forward to your talk.
Awesome, yeah. Hey, I'm Omiros Montazis. Very excited and glad to be here in Computer Vision Talks, giving this talk. Yeah, as you mentioned, I'm a PhD candidate at UCL, and the particular talk I'm gonna focus today is gonna be about vision language model adaptation, and particularly our published paper that utilizes self-supervision to adapt large pre-trained models like LIP to challenging visual tasks. And this work was a joint effort between myself, Gabriel Brosto, and Kay Jones from UCL, and Austin McKay from the University of Edinburgh. Okay, I'm gonna start with a small overview of our work and the achievements, and then I'm gonna dig a bit deeper into details and explain the background, etc. Okay. So yeah, recent successes in large vision language modeling exploit the vast amount of data that are freely available on the web. And they do this by forming a pre-training task that utilizes them with the goal of predicting drivers, like ranging from bird breed recognition or medical image classification. And in order for us to maximize the performance, like vision language models like CLIP need to be further adapted. Like it's a good basis, but further adaptation always helps reach the maximum performance possible. And as you may know, a common way to build on top of the knowledge learned by a large pre-trained model in general, not only vision language ones, is to adapt the new visual tasks by fine-tuning them with data from the desired task, and thus improve the downstream performance this way. However, as you imagine, like this can get challenging because of the computational costs that are involved in tuning models of large size. Not anyone can train clip from scratch, or like you can imagine the equivalent of a language model like GPT. So there have been some alternative approaches that address this issue by proposing lightweight adapter modules and get trained efficiently on top of frozen features. But even this can fall short on challenging visual tasks that differ significantly from the style of the internet data um, that the visual language model has been trained with in the first place. So to tackle this aforementioned shortcoming in vision language model adaptation, we proposed SVL-Adapter, which actually is a method that uses self-supervised learning on the challenging downstream tasks themselves in order to assist the adaptation of the procedure on this task. And yeah, I mean, in a nutshell, like after evaluating SVL-Adapter on a set of challenging visual tasks, we observed that we can get about 10% average accuracy boost on top of existing vision language adaptation baselines by combining the two essentially. So yeah, but this was the small overview. Now let's take a step back and try to understand why vision language models are interesting in the first place. So learning transferable representations of visual data has been a core problem in computer vision, and until recently, the standard approach for tasks like supervised image classification involved training models to predict the discrete class labels depicted in a collection of images, such as ImageNet, for example, and followed by a stage that fine-tunes the model weights to the downstream task itself. However, as you can imagine, like this approach typically relies on a laborious annotation process, first to generate labels that tackle the narrow task, and thus making the adaptation to a wide variety of tasks not so intuitive. Um, and for this reason, like the visual representation learning paradigm starts to shift away from datasets that have explicit class labels, such as ImageNet. On the other hand, like we have the availability of huge amounts of image and text pairs that are typically found on the internet, which constitute a great source of training signal that can be exploited by alternative approaches. And specifically, lots of methods now exploit the natural language that accompanies internet images as a loose form of supervision within a joint vision language modeling task. So learning from such unstructured data collections can really help scaling up models and gain on inference power because there is no restriction on how many images we need to label. Here we mention like some representative vision language models that have been proposed recently as a reference because more and more of them are coming out as we speak probably. So yeah, one of them is Clip, as you probably know, and indicatively like Clip exploits 400 million curated image text pairs retrieved from the web and forms a contrastive task between the corresponding visual and text embeddings. And a similar approach named Align, the authors constructed a quite similar task, contrastive as well, but they used an uncurated dataset instead, which
Hi, Amir. Sorry to disturb. There are a few concerns in the chat that people cannot see the video of the slides. Do you want to reshare it? I'll pause the recording.
So yeah, as I mentioned, like another approach named Align actually follows the contrastive learning paradigm of Clip, but the authors instead use an uncurated dataset instead, which, as you can imagine, can enable scaling up vision language model pretraining to larger sizes because there's no need for a curation stage between collection and training. And they were able in this way to scale up to 1 billion image text pairs. And meanwhile, like this other approach, Flava, does not constrain on the formation of a single contrastive task between vision language pairs, but instead they utilize a wider range of pre-training tasks around various modalities. And yeah, the best versions of this approach is use the successful vision and language transformers as their backbone architectures, which is starting to becoming a trend right now. So for our research and the adaptation experiments, we focused on CLIP, as it is quite representative of the recent vision language modeling approaches, but we consider our approach quite orthogonal to the underlying vision language model, so it could be used with the others as well. So yeah, let's start with it. So the main assumption behind models like CLIP is that text and images represent two different modalities that are able to capture different contexts of the same object. Here we see, for example, an image of a puppy along with a caption that puts the content of the image in context. So essentially the text that accompanies the image is the context. So pre-training on hundreds of millions of text and image pairs like this one has shown huge potential on tackling relatively well a variety of visual classification tasks in either zero shot or low shot fashion, which is either without any new samples at all or only a few. And then being able to do well on the task at hand, the task of interest, the final task, if you want to say so. And now let's take a look into CLIP, which is the vision language model of choice here, and see how it exploits internet data to improve its zero shot and low shot classification performance. Okay, so we have unfiltered, highly noised and varied image and text pairs that are retrieved from the internet, and Clip managed to exploit their signal to learn general representations with the ability to transfer. I mean, this is their proposition. And how they do this? They do it by applying a contrastive learning in the embedding extracted via respective visual and text encoders of the network. The pre-training task essentially leads to vision and language encoders that can be used to extract general features on the desired end task. So a pre-trained Clip model that has been trained on such a contrastive way can then, during inference, be instructed in language to perform a variety of classification tasks without directly optimizing for them. And this is done by first providing a set of candidate classes that are encoded via the pre-trained text encoder. And meanwhile, images for the given task are passed through the pre-trained Clip visual encoder. Finally, the zero-shot prediction from the vision language models correspond to the class text embedding that was closer to the embedding of the given image. And recent works show that vision language models can sometimes exhibit a very, very good zero-shot image classification performance. That means without any images at all. Yeah, here that's from the Clip website, and we see some images and candidate class prompts coming from a variety of downstream tasks. And we see an illustration of how they demonstrate their generality, if you want to say so. Like we see different tasks here with completely different associated classes and thus prompts. And yeah, it does impressively well. The problem is that fine-tuning pre-trained vision language models to further increase their performance on a queue task can be, as I told you, expensive because of the costs involved. And there may be some generic tasks like that that the model can adapt for the majority of the cases, but to perfect them and make them catch every single case, or if you want to say so, get away from the internet paradigm needs more effort. And a scalable paradigm has been freezing the backbone and then um, building on top of that, like with a smaller network that is more easy to train. So yeah, now I'm going to talk about some approaches that have been out there and tackled the issue of tuning with a few images instead of tuning the whole architecture with more. So yeah, inspired by work in natural language processing, which is a couple of years ahead on that aspect, there are a series of methods that have been proposed to adapt large-scale pre-trained vision language models in a data-efficient manner. And they do so by keeping the text and image encoder fixed or frozen, and given a few samples of labeled data, they have lightweight components that are trained for the final image classification task. An example, the few images that become available per class can be used to optimize for the most effective context words to be used in the downstream task prompt. While some subsequent works like use the few annotated images to refine the learned representation by appending trainable adapter networks on top of the features such as the ones extracted from clip. And yeah, these methods have proven to be effective on transferring to some tasks. However, the fact that they do not significantly change the underlying visual representations that come with a pre-trained vision language model, that may compromise the generalization to new tasks that differ significantly from the original internet dataset that CLIP has been trained with. But yeah, you may wonder why we want vision language models to adapt to tasks that do not share the internet characteristics. And it's going to help us to take a look into a real world use case that, for example, stresses this need for fast adaptation, why we need to adapt fast from the models that are out there. So there has been, as you know, like some rapid deterioration in our environment, which demands efficient monitoring solutions in order to evaluate the impact of either government or institutional policies and act fast to protect our nature. So there's a huge need for models that can generalize with minor efforts to such tasks. At the same time, the data that are usually collected for such efforts, like biodiversity monitoring, tend to be imbalanced, visually imperfect, and quite unique. For example, like it's common to deal with blurry, occluded, or partial views of objects across diverse backgrounds on ecosystems. This doesn't sound a lot like internet data, right? But that makes the representations from such visual language models to not be able to transfer properly to such tasks, at least not with an extra effort. And understanding this problem and to test the limits of the current vision language model adaptation methods, we introduced here a set of challenging datasets that correspond to real-world tasks, which include biodiversity monitoring from camera traps, optical tomography medical imaging, and remote sensing from satellite data. In this collage, for example, we see an extending set of images coming from the aforementioned real-world tasks, and it becomes clear that these datasets are imperfect and have a variety that can't be covered from the typical type of data found on the web. In contrast, these are the dataset that vision language adapters have until now been evaluated with, that mostly resemble the internet style. The bunch of photos you see here kind of stress the point that even though we see some diversity within these datasets, the images tend to be quite centered, quite high definition, and in general easier to adapt given the fact that you have been trained with an internet model. And as a matter of fact, we visualize how confidence scores of zero-shot clip can vary with the type of the downstream task. On the left side, we see clip to be quite confident when applied to a typical internet style dataset with pets, while its confidence drops significantly for images of species capturing camera traps, so in the wild. And it's fair to assume that in order to test the transfer capabilities of CLIP in a more realistic manner, one should utilize datasets that differ from the content found online. In order to assist this adaptation of large-scale pre-trained vision language models to a challenging end task, we propose to utilize targeted self-supervised learning on data from the task itself. The first step in our approach is to exploit the recent advances that are out there in self-supervised learning to learn representations that are relevant to the downstream task. And this can be done by pushing together embeddings of task images and their augmented versions during a pretext task. In particular, like we use SimCLR here as a representative of the latest developments in self-supervised learning for visual tasks. And in a few short fashion, we make available a limited amount of images per class to train an adapter network on top of the frozen self-supervised features, which are extracted by the encoder from the first step we trained before, mentioned in the one slide before. And during inference, we get outputs by passing the images through the adapter network. In addition, here is where clip comes in. In order to exploit the zero-shot transfer performance of clip and complement the output of the adapter network, we also pass images and class names through the pre-trained clip visual and text encoders respectively. Finally, we combine the outputs of zero-shot clip and the adapter network. And for the optimal combination of the self-supervised adapter outputs and the clip zero-shot prediction, we use the fusion parameter. And this fusion parameter is traditionally picked by using a held-out validation set. Here, like we also deploy a fully automatic way of selecting this blending hyperparameter that is analogous to the confidence scores of clip. And we termed this approach SVL-Adapter star. Okay, so in order to evaluate the adaptation performance of SVL-Adapter, we introduced 6 challenging tasks mentioned above, along with 10 more conventional datasets typically utilized by vision language adapters. We deployed different amounts of supervision in the form of few-shot learning and compared our approach with zero-shot and linear probe clip, along with the state-of-the-art visual language adaptation baselines that are out there. Here we see a comparison of the top 1 accuracy averaged over the 16 tasks I mentioned before. The colored lines represent each of the baseline methods evaluated, and the amount of supervision is varied on the horizontal axis. So this is number of images available per class. We observe that the green line, SVL-Adapter, illustrated in dotted lines for the SVL-Adapter Plus, consistently score higher than the best performing baseline, which is tip adapter F here, under different numbers of available training examples per class. And what's more interesting is that we see that SVL-Adapter star is very close to SVL-Adapter, despite not requiring an extra validation set to tune these blending hyperparameters. By the way, this is something most of the approaches did, like a tip adapter and clip adapter. They use some extra labels, even though they term it two-shot learning. Usually they need some extra images in order to define the blending hyperparameter. So here we show that this can be done by in an automatic way that's analogous to the clip confidence, as I mentioned before. And what's more important, and the main focus of our point here, is that when we steer the focus of our evaluation on the challenging tasks, we confirm that current visual language adaptation techniques still perform poorly, with the top performing baseline reporting less than 50% accuracy on average in the 16-shot setting, for example. And to this end, we show that SVL-Adapter, which uses the self-supervised features as well as a starting point for visual adaptation, leads to a significant accuracy gain of about 10% on average in the challenging tasks. And that's when compared with existing methods out there. And moreover, like we also tested a zero-shot version of SVL-Adapter where clip pseudo labels replaced the few shots, and we report quite significant gains when compared to the predictions that came out straight of zero-shot clip. So basically here we compare zero-shot clip, which is the gray star, with a version of SVL-Adapter that uses pseudo labels produced by clip itself. And yeah, it's impressive that without labels, you can get this boost just by seeing the visuals learned by the self-supervised learning task. And in one of our ablation experiments we exploited one of our previous self-supervised learning works to show that the performance of SVL-Adapter can improve even further when better self-supervised features are used instead of simple SimCLR. And in this preceding ICCV paper, we had shown that exploitation of contextual information in order to select positives for a self-supervised method such as SimCLR significantly improves the performance comparing to naive self-augmentations of the images. The gains were also present when the SSL features of SVL-Adapter were extracted on the aforementioned way for biodiversity monitoring datasets that we tried it on. And basically in this way, we show that in an empirical way that better self-supervised features also improve the adaptation performance. Moreover, like the same stands true for other components of the network, with the performance improving when deeper clip architectures are used instead of the ResNet 51. So we can conclude that the SVL-Adapter framework is quite flexible and can benefit from developments of both ends, given that replacing with a better self-supervised feature model gives benefits, replacing with a better zero-shot vision language model gives benefits. And finally, we also observe that the fusion is quite important here. Like using the self-supervised features themselves didn't give the performance gains that we got with the fusion across all the tasks. Okay, now to summarize, we tested the limits of vision language model adaptation by introducing challenging datasets, and we showed that current baselines struggle to adapt on this. And on that end, we also presented our method, SVL-Adapter, as a way to combine the best of both large-scale vision language pretraining, algorithms such as CLIP, and targeted self-supervised learning. We also showed how this fusion can be done without the need for a held-out validation set. That's with a blending hyperparameter automatically learned by as analogous to the confidence scores of CLIP. And after detailed evaluation on about 10 standard and 6 challenging datasets, we showed that SVL-Adapter can outperform existing methods on average for both zero-shot and low-shot learning. And this seems to be significantly better on challenging datasets whose visual properties, as I explained before, differ from those ones commonly found online. Of course, there are more results and ablations, and you can check our paper and supplementary material for this. There's an archive link here, but I think there was also one accompanying the talk in case you want to learn more. And we also made our code available on the GitHub link, on the following GitHub link, in case you want to try it out on your own datasets or try it on your own overall. That concludes my talk. Thanks a lot.
Okay. Am I audible?
Yes, Shambhavi, you are audible. Yeah.
Okay. So it seems my internet dropped at the very last moment towards the conclusion of the talk. So thank you. It was very explanatory. And Nikhil, do you mind reading out the questions from the chat, because my chat has disappeared and there were 2 or 3 of them. I remember one question was talking about the computational cost of the models as they were pretty large. So did you do a study to compare them?
Yes, you actually mean the downstream task adaptation, right? Not the clip itself.
No.
Yeah, so it was super fast because we're talking about 1, 2, 4, 8 shots per class, and we only trained for about 50 epochs.
Okay.
I'm not remembering the exact time, but it was in the magnitude of a few minutes.
Okay, great. So that answers the question. And there was another question from Kunal. Nikhil, can you read that out? I'm also asking Kunal to unmute himself if he wants to discuss it with you.
Yeah, the question is, what is the data source? How is the text image pairs obtained? I believe they are not human verified. Is there label noise?
Yeah, that's a good question. Actually, that's what differentiates a clip and align. So clip is using pairs, image text pairs obtained from the web. Of course, initially there's quite a lot of noise there, but according to the authors of the paper, they say that they have curated it before doing the contrastive learning with the 400 million images. On the other hand, Align, which we didn't use on this paper, use a more noisy version. And however, they were able to scale up because of the fact that they haven't curated it. And the point, I think, of this paper was that even though they may be noisy, there is robustness when you have lots of images on the training task.
That's right. Kunal, does that answer your question? Do you have anything else to ask? And if anyone else has questions, you can put it in the chat box. I'll proceed with the generic questions till then. And okay, it answers Kunal. So yeah, have you been working on this pre-training and self-supervision model since long? Or was this your first one?
For visual language model specifically, this was the first year I played around with. But self-supervised learning has been a theme from the beginning of my PhD. So yeah, as I mentioned towards the end, our previous work was focusing on self-supervised learning, and particularly for biodiversity monitoring datasets, because I believe these are a good test bed to show some of the inefficiencies of current approaches and how like current benchmarks don't cover some use cases that need to be covered.
Okay. Great. Any other questions? Go in the chat box or just raise your hand to ask the question because okay. So next question was like okay. Yeah.
Yeah. So there is a lot of discussion on the fairness of these models, right? So have you done any experiments on, because large language models and these are very huge models. So is there any experiments which are done on fairness component of this?
No, not for this particular work. That's a great point though. The reason why we didn't do such fairness experiments is that usually this is around the underlying model, like the initial, like let's say clip pre-trained features that are debiased, if you want to say so. In our case, we are taking the representation learning part for granted, and we try to do the visual adaptation in terms of performance, making it work better. So if we were to, because this is not our field of research, but if we were to use it, let's say for a real world application, we would debias the initial like clip model and then do our adaptation part. But the adaptation part is quite independent of what features are you coming from. So yeah, definitely very interesting. Not the goal of this particular project.
Right. Okay. So another question that I had was, Nikhil, are you saying something? I'm sorry.
No, I got it.
Okay. Another question that I had was, what were the drawbacks of clip that you figured out while doing this incremental or work in adapting it for another task?
Yeah, actually, this was the inspiration for this method. The downsides were actually that as long as we were shifting away from the visuals of the internet data, which means like starting to have blurry images or imperfect objects, hiding objects occluded, or parts of the animals, for example, being visible instead of the whole animal, then it started suffering because there was a lot of uncertainty, and you could see it on the confidences of clip even without evaluating. It was degrading heavily even within datasets to from the parts of the dataset that were more hard, like there was some occlusion, for example, between animals, and then it was not sure about the underlying label. And another one that came out was that it was not growing greatly when expertise was needed. For example, fine-grained recognition of between two species that are that an expert needs to have some exact visual knowledge about their visuals to classify them. So particular types of gazelles, for example, it may struggle because in the internet it may have seen images of gazelles overall, but not the particular subspecies of gazelles. So I would say in a nutshell, like fine-grained recognition and um, the domain adaptation between internet style and non-internet style, which is more rough.
Right, I can understand parts of it because I remember in a talk that we were having, Bala, he has also put a question in the chat box. He was showing some of the results he got from clip models. So they were quite interesting as well and had the same problems that you were mentioning. So Bala is asking, can you explain more about prompt templates? I see there's a section explaining it in the appendix. Okay, Bala has read the appendix as well.
That's flattering. Yeah, so the prompt templates we used were quite basic here because our point was that you don't need to do extra work there as long as you adapt the visual part. Of course, like a perfect model could benefit from tuning this as well. I think it could be even better if I, for example, combined our approach with co-op and the ones I use, for example, for the challenging tasks, for the non-challenging tasks, if you want to say so, were the ones that the preceding approaches used, like a clip adapter and a tip adapter. And for the challenging task, I try to use the most general one I could think of in order to not ingest any form of expertise inside the prompt. So it was like, this is an image of something instead of this is an image of particular type of animal found in the African Sahara. So I try to not to give context around the particular task.
Does that answer your question?
Thanks for that. And then like you have done something on this OCT classification, right? It is something on a medical image classification data set. So like, why do you think that has worked? Because, you have replaced it with, for example, like instead of using an abbreviation, you have told that instead of CNV, we have used it as a choroidal neovascularization instead of BMV. Yeah. So like, did you observe any differences? Like instead of using CNV, do you really think that, using this kind of, abbreviated thing made improvements?
This is a good point. Yeah, this is not the prompt itself, but it's how you represent the class.
Exactly.
Actually.
I mean, by prompt, I mean the same full sentence. Yeah.
Okay. Yeah. So yeah, that's a good point. We needed to replace this with a full word because internet is full of acronyms, and there could be multiple other things that can found in the internet that had the same acronym. So in these cases, and I know this is a particular case, but this kind of case exists. It's important to try to make it as clear as possible.
Sure. So now, like, this self-supervision thing, right? And then you have this adapter in the end. But before that, we have both the image and text encoders, no? So the text information which we are giving through this, like choroidal CNV or things like that. So now it's basically the final layers, the self-supervised layers will, whatever representation which has been learned, the semantics and the language thing, it will be combined here, right? Like it is more like a fully connected layer in a ResNet. Can I think like that? Like, is my thought process fine or?
Yeah, so if I understand correctly, you're right that the adaptation takes place only on the self-supervised features.
Yes, yeah.
And clip is kept zero-shot as a complementary approach.
Correct, yeah. Yeah, okay, fine. Yeah, I got it. I got the idea. So yeah, because since we are kind of freezing both the image encoder and text encoder from the clip, yeah, okay, got it. So it's amazing that the words like this were able to like made sense for the clip model at all. So that is actually amazing for me.
Yeah, and even the self-supervised encoder is frozen on the downstream task. So
sure.
any encoder is frozen. So the only thing that is trainable is the mini adapter on the end.
Yeah, got it. Thanks for the explanation. It was very useful for me.
No problem at all.
So Bala has definitely brought out the good parts of your work. I have one question, which I wouldn't have asked if I was not a PhD student myself. So this is an approach that worked for you and ended up into a paper. Was this the first intuition you got to work on, or were there other experiments that you tried and didn't work and you landed up on this one?
For this particular work, to be honest, no. It helped a lot that in my preceding works, I have already dealt with such datasets like camera trap images. And I kind of knew already the problems that conventional computer vision approaches have. So this project started as an experimentation around, let's say, like the newest thing out there for representation learning. And this was CLIP, for example. Does it work with such real-world datasets? And that's where we also compared it with benchmark datasets that were used so far, and we saw this big difference performance, like without even considering the with the existing base, without considering the baselines, even with CLIP itself, we saw the zero-shot performance degrading and its confidence degrading. So it was kind of obvious for us to think for ways to restore it. And self-supervised was an intuitive first try for us, given that we, in the ICCV paper, we have seen that it can benefit biodiversity monitoring images and datasets.
Interesting. Okay, so I don't think there are more questions in the chat. If there's any, just put them quickly up down there. Apart from that, we've already had a great discussion. We have our answers, and it was a very simple yet a solution that worked out really well for you. So it was a good paper. And okay, so there are no more questions I see. And last question, how long did it take for you to pan out the paper?
Sorry, to what? To write the paper?
To complete the paper, like starting from the experiments till the end of it. How long was it?
Think about it. So it was 4 or 5 months, I think.
And were there any concerns from the reviewers?
There were concerns, as always. There were always a mixture of reviewers that some make you feel good, some make you feel bad, and you need to reassure the ones that were not so happy that your specific target and how you differentiate with existing methods, why you mentioned that, why you didn't mention that. So I think it was a typical round of, I'm not certain that the paper is going to be accepted because there's a mix of reviews, and then because every reviewer comes from their point of view as well. So you try to explain to them within a single PDF.
Satisfy all of them,
Not only satisfy, but kind of explain why you think this is a good contribution. Because spending 4 or 5 months, as you said, versus spending 2 days reviewing might not give you the full picture. So trying to explain as much as possible.
This question came because usually there's one or two interesting question and reviewer has a massive problem with it in understanding. Like I remember one of the authors shared that the reviewer could not understand the mathematical notations of open and close bracket and had raised a concern. So this question gets us comic answers. That's why I posted it. But thank you so much for thank you so much for joining us today. It was a great talk.
Thanks for having me. Like, this is amazing. Yeah, thanks for organizing all these interesting talks, and your channel is some channel that people should follow in the field, especially computer vision.
Thank you so much. I have not worked too much on getting it more to the audience. That's the goal for this year. So I'm on it. Thank you so much. We look forward to greater work from you. Thank you. Bye-bye.
Awesome. Yeah. Bye-bye.
Have a nice weekend.
You too.